When they come up, I'll just introduce the first person, which is going to be Bryn. Okay, so I'll read Bryn's introduction here. So Bryn's a hydrogeologist with the Oregon Department of Environmental Quality based in Eugene. He has been the DEQ's project manager for cleanup of several former Mercury mines in Oregon and of Black Butte Mine since 2003. He has a Bachelor of Science in Geology from OSU and worked in environmental consulting until 1998 when he was hired by the DEQ. In addition to managing the cleanup of several Mercury mines in Oregon, he also participates in international cleanup of Mercury contaminated sites. All right, so with that, I'm going to give the mic to Bryn. Thanks, everybody.
I didn't know you were going to do that. Thanks a lot, Maggie. Real quick plug for the council. I've worked with these folks since 2000-ish time frame on the Black Butte Mine, and as a regulatory person, sometimes it's hard to connect with some of the landowners and some of what's going on out there. And the watershed councils they're the people that you can connect with because they're out here, they're meeting with people, they're meeting with landowners. They're an excellent organization, so please support them. So today we're going to talk about Mercury, we're going to talk about Black Butte Mine, we're going to talk about Cottage Grove Reservoir, and I'll quickly introduce the other speakers right now so that we can get along with this. But we've got Dave Tomten, who is the project manager from EPA, who is leading the cleanup at Black Butte Mine. There's myself, and then there's Howard Young, who is a contractor working for EPA. He's been working on the project for, I don't know, probably 10 or so years. And then Chris Eckley, who is a geochemist that's been working with EPA for a number of years. He's super smart, and he's going to present stuff about Cottage Grove Reservoir, which is it's going to be kind of fun. There might be some nuggets in there that get a little too sciencey, but bear with us. And I'll mention really quickly on the trivia questions, I came up with most of those, and I heard some of my colleagues here in the room kind of like, that's not quite right. So I'm not going to go there, but we can talk about it later. All of us will be here after the meeting, or the presentation. We're going to have Q&A, but we'll be around for a little bit after that if you have some individual questions. So today we're going to talk about mercury basics, some toxicity information, the global context, how this kind of is connected with the global picture of mercury. Then Howard's going to talk about Black Butte Mine history, cleanup history, and what they know about Black Butte Mine and some of the assessment work that's gone on in the last few years. And then Chris is going to talk about Cottage Grove Reservoir, methylation, and some of those really interesting sciencey things about the benthic community and how things are moving up through the food chain. And then Dave's going to talk about the next steps, about the cleanup that's going to take place next summer. And that's it. Let's get going. So the basics, we've went over some of this already with the trivia questions, but mercury, Hg, its atomic number is 80. It's located down here by gold and thallium and lead. So if you think about, if you've never played with mercury, and I think maybe some people probably have here, but if you feel the weight of mercury, it's basically like holding if you had a small amount of it, it'd be similar to holding like a fish weight, like a lead weight, because it's pretty similar to that. Not a lot of us have held much gold, probably, like a fish weight. Atomic weight, we went over that. It's called quicksilver. The Latin term is hydrargyrum. I think that's how you pronounce it. Basically, that means water, silver, very similar to the term quicksilver. And the very interesting thing about mercury is that it's a liquid at standard temperature and pressure, and that's what people from many eons ago, alchemists and all that, were very interested in mercury because it was very sort of spiritual and interesting and weird that way, unlike a lot of other chemicals. And we already went over, or elements. Already went over the NFL player. Mercury ore is cinnabar, HGS. That's a mercury element, mercury atom connected to a sulfur atom. There's a few other types of compounds that come out of mercury ore, but generally speaking, cinnabar is it. And you have about 0.1% of mercury in typical ore. And we can kind of calculate that out into milligrams per kilogram. And what we do find actually is around the area of contamination at the mine site, you'll actually come across areas that are similar to that type of concentration. It's emplaced in the earth generally through hydrothermal alteration. Well, basically hydrothermal fluids come up through the fractures and they basically precipitate out a variety of different heavy metals. And mercury and arsenic and oftentimes lead are often commonly together in those hydrothermal emplacement areas. And sometimes you actually get native mercury or liquid mercury in the ore. It's not very common, but some folks have seen it in various areas. Almad in Spain and maybe in Santa Barbara, Peru, are some of those locations where it's very concentrated. You may actually see it there. And the process, essentially what you do is you want to break the mercury-sulfur bond. So what you have to do is basically heat up the ore, crush it to a finer grain, somewhere in the 3/4 minus arena, and then you run it through a heater to 600 degrees C, and you get an exhaust that comes off of that is full of elemental mercury in the exhaust. Then you can distill that down much like you would with alcohol or whiskey or something like that. And then you collect the liquid mercury at the bottom of that. Sorry.
Boiling point of mercury? What's the boiling point of mercury?
I'm not sure. I don't remember that one. It's probably. Well, that'd be, yeah. So it's actually volatilizing at standard temperature and pressure. So it'd be, but anyway, let's talk about that. So anyway, and real quick, interesting little tidbit is that there are some people now studying when humans actually started retorting or refining mercury from not just using cinnabar as pigment, red pigment, but actually cooking it and getting elemental mercury to use for gold amalgamation or other things. And there's some thoughts that maybe the Incas did before the colonial Spanish showed up. And there's some looking into some work in Mesopotamia, like Babylon and some of that area, and even Egypt. So that's kind of fun to watch that research take place. Here is a quick picture out of Quicksilver, Oregon. It's a really good document from 1930s USGS, well actually it's Bureau of Mines, that presents a lot of information about the various mercury mines in Oregon. And the left picture here shows the condensation equipment. So these are terracotta tiles that have been laid up at a sort of an angle, and the exhaust flows up through those, and the cool air around the outside essentially basically condenses the mercury on the inside, and it comes down to the bottom, and you collect it. On the right side here is a picture of the stack, and it's not hard to see in here, but in the original photo, there's all this kind of smoky material kind of flowing out of that, and I'm assuming that that's maybe a mixture of wood smoke along with mercury. And there's been reports from some of these that back in the day that there was needles on the fir trees outside of these that had basically silver droplets on them, and they were kind of covered in silver. So you can tell that that was maybe a somewhat inefficient process. And just to put us in the context of what we know about Oregon, there's quite a number of mercury mines in Oregon, just like in California, Nevada, Idaho, and Alaska, all around Washington. Some of the main districts are the Black Butte Elkhead district. There's a mine on the other side of the drainage. You probably know about that, Elkhead mine. And then further south by Sutherland is the Bonanza Nonpareil area. And Bonanza mine was another big mine, just like Black Butte mine. Those two were pretty large producers in Oregon's mercury history. There was also a number of mines out in the east, up in the Ochoco's and down by the farthest southeast corner, way down there, McDermott. So toxicity, there's two exposure pathways that we focus in on. One is inhalation and one is ingestion of organic mercury. On this slide, I'm going to talk about the inhalation aspect. We all know about the Mad Hatter. That's one of the earliest sort of well-known, obvious sort of poisoning sort of things that took place. This picture in the middle are hatters in England that were essentially putting the felt for the hats in a mercury nitrate solution, and as they heated it up, the mercury would come up, volatilize out of there, and they were breathing that in, and so they became basically mad as a hatter. And then today, one of the common exposure pathways that we see in the world and in developing countries is artisanal and small-scale gold mining, where people are using elemental mercury for gold amalgamation, and they're essentially just breathing that vapor in. They're also retorting it or cooking it off. Sometimes in stores or sometimes in homes and that kind of thing. So that's a pretty serious issue. And then the organic mercury part, where you're ingesting organic mercury, it caused some very severe issues back in the 50s in Minnesota, where you get deformities. It looked like it was a congenital type of thing, where you were getting effects through the mother to the child. And several thousand people were affected by that. And that was kind of this sort of Rachel Carson thing for mercury. This is when people were like, wow, this is a serious issue. Eugene Smith collection is a really, you've probably seen some of those photos, but it's very touching and pretty hard to see. But basically, it really brought on this idea that mercury's serious. This is bad. Basically, what was happening was that methyl mercury was going into Minamata Bay, and people were eating the shellfish and the fish in that area, and they weren't really aware of it, and they just had all these effects. On the right here is just sort of a list of a bunch of other sort of significant sort of mercury events or mercury studies or things like that that we've seen over the years. I want to emphasize that the UNEP Environment Program now, since 2013, has engaged the Minamata Convention, which essentially is getting all of the countries, trying to get all the countries in the world, just like the Kyoto Convention for climate change, to get all the countries in the world to basically stop the use of mercury. And red rice disease was one of those silly questions I had on there. But basically, there was an Iraqi incident in the 70s where people ate a fungicide-laced seed. They were supposed to plant it, but they actually ate it because they were hungry and didn't see the labels, didn't read the labels, and about 400 people died from that. So mercury, from a global perspective, we're seeing now that artisanal small-scale gold mining is the largest source for atmospheric inputs. Naturally occurring volcanic may still be there. I'm not quite sure. We haven't looked at all that, but anthropogenically, that's the biggest source. It used to be coal-fired power, but I think because we've got better systems for that now, and because of sort of that gold rush that took place in the 2000s in the international community, we've seen a lot of that take place, the artisanal and small-scale gold. And then from a regional perspective, a lot of this comes from Southeast Asia. Probably a lot of that's from coal fire. The two green and orange up there are the South America and Sub-Saharan Africa, and those are predominantly from artisanal and small-scale gold mining. And so these last two slides before I hand it over, but this is essentially a figure presenting the total mercury concentrations in precipitation in the United States. These are like average concentrations over a period of time. And what we're seeing here is that in the West Coast, we're seeing greenish, not a lot of contaminated airfall or contaminated precipitation falling in that area. But when you look at the amount of rainfall we get in Oregon, this is to demonstrate that there is a high load just because of the rainfall. So we have a lot of rainfall, and it's not highly contaminated, but because it's continually raining in the Willamette Valley and on the West Coast, you get a pretty high load of mercury just from the atmospheric deposition. So I hope I didn't go too fast, but that's my stuff. I'm going to hand it over to Howard with CDM Smith. He's the contractor that works with EPA. He's been doing a lot of work, kind of similar capacity as me, a geologist out of their Seattle office, and he's going to walk through some of the sort of the details about the assessment work and the cleanup chronology and some of that. Thanks.
All right, thanks, Bryn. I'm going to talk a little bit about a more local issue with the Cottage Grove Reservoir and the Black Butte Mine. So this slide here on the right shows a map of with the Cottage Grove Lake up on the north, about 10 miles upstream on the Coast Fork. In the box there is the location of the Black Butte Mine. Back in, I think as early as the 70s, I think they had found, levels of mercury in the fish of Cottage Grove Reservoir that were of concern. So this prompted Oregon Department of Environmental Quality and EPA to look into sources. And Black Butte Mine was the only really developed mine in the watershed, so that was what was assessed. On the left side, there's a little box showing the conceptual site model for how contamination from the Black Butte Mine gets into the watershed. Kind of the most simplest explanation of that is that when you have precipitation Storm events, you have erosion of mercury bearing soils and tailings getting into the creeks that drain the site, and then they're transported downstream in the Coast Fork, and then where they drop out in the Cottage Grove Reservoir. So this slide just shows on the left a historic sketch of what the mine looked like, at the turn of the century. And on the left is a shaded relief map showing, showing the present day topography and the historic features. So basically the Black Butte Mine site it's bound on the north by Dennis Creek, and on the south by Furnace Creek, a much smaller stream. And then on the west side, you've got Garroot Creek, which receives, the discharge from Furnace and Dennis Creek and flows into the Coast Fork of the Willamette into the reservoir. So the main features of the site, kind of in the upper elevations of the site, there's an underground mine working, the cinnabar deposits along a fault zone. They're shown in yellow. And then the way that they operated the mine was they mined underground, crushed the ore, and then transported it down the slope to the ore processing areas, which consisted of crushers and ore furnaces to extract the mercury. So at one time there was an aerial tramway which brought the ore down to the furnaces, and then later they had a small railroad that transported the ore. And then there were at least 2 furnace sites where the ore was processed and mercury extracted, and the waste rock from that process was just deposited in these large tailings dumps. And those are shown in kind of the green shaded area and the light brown shaded area. And I guess the point of this slide is to show that we got a pretty extensive area with tailings, and they extend right down into Dennis Creek and Furnace Creek. And this is just a photo from the north looking south at the mine site, so you can kind of see with the arrow on the left kind of the extent of where the underground workings are at. And then the ore processing area was down here, and the shaded, or the oval area there is where we've got tailings. But it looks a lot different than it did during operations of the mine. It's basically been, dormant for 50 years, and so the site area is pretty overgrown with trees and brush. So about 2012, EPA started the remedial investigation of the site. There had been some work done earlier just to identify, that this was a problem and what medias were affected. But the more detailed remedial investigation started in 2012. And the way it was done was we looked at the site by media that was affected by the mine. So we looked at surface water and groundwater, and we also looked at stream sediments in these 3 creeks. And then we looked at the actual source areas at the site, the mine tailings, the waste rock dumps, and impacted soils. So this is a map similar to the other one, shaded relief map. Shows Dennis Creek on the north, Furnace Creek on the south, and then Garroot Creek on the west, on the left side of the figure. This is just showing how we approached the surface water investigation. We established monitoring stations at the mouth of Furnace Creek and Dennis Creek, and on Garroot Creek upstream and downstream of the mine. And we sampled, surface water for mercury and other metals during storm events. I think we did a total of 6 surface water sampling events during storms, and then we also sampled it during non-storm periods to just see what the baseline was of metals loading was during just ambient conditions. And then shown kind of with the checkered red and white dots, those are the groundwater monitorings that were wells that were installed as part of the groundwater investigation. We wanted to see if this big pile of mine tailings had been had resulted in any leaching of mercury and an impact to groundwater. So I think there was a total of 11 shallow groundwater monitoring wells installed, in the mine area and in the floodplain between the mine and the river. And those wells were sampled, I think, during 3 different monitoring events. So this is a chart showing kind of the results of the surface water sampling at each of those creeks. It's just showing one of the baseline events and then 3 stormwater events. So the y-axis, you have total mercury concentrations in surface water. And then each of the bars, the different colors represent different monitoring stations. But the point of the slide is that you can see over on the left, the baseline event, which was a non-storm conditions during the summertime. We had very low mercury concentrations in all of the creeks. And you notice that there isn't any data for Furnace Creek, which is the red bar in the other events, and that's because Furnace Creek is only flows during the winter, during the wet season. So the main point of this slide and the results of our surface water monitoring was that during the storm events, you see this red bar, which represents Furnace Creek, is very high mercury concentrations. And the blue and the orange are the other creeks, and they're relatively low compared to Furnace Creek. So it was kind of an indication that Furnace Creek, even though it only flows part of the year and it has the lowest flow of the site, was an area where there was very high mercury concentration. So that was a big finding of the work. So we looked at all of the surface water sampling events together, and we looked at how much water was flowing in each of those creeks throughout the year and what the concentrations were to get a loading estimate of loading of mercury to the watershed. And then we looked at it for each of the creeks, how much mercury was being contributed by each of the creeks. And so the point of this slide is to show that the large green area is the contribution from Furnace Creek. And even though it's an ephemeral stream, only flows about 6 months out of the year and has very low flow rates, the concentrations were so high that it was actually contributing about 50% of the mercury loading to the watershed. So Furnace Creek was kind of the focus of the investigation. We also looked at, what was the form of mercury in surface water downstream of the site. So we did this looking at what's the total mercury concentration in surface water and what is the dissolved concentration. And so what this gives us is an idea of how much of the mercury is coming from suspended sediment in the river during storms, and how much is just dissolved in there. So you can see here that the blue bars are the majority of the mercury, and that is the suspended load phase of mercury, and the red area, which is a much smaller percentage, is dissolved phase. This was kind of an important finding because it gives us an idea of what the source, what's causing the mercury to go downstream, and ideas on how to remediate it. So after we had completed the surface water and groundwater investigations, we needed to focus on the mine site itself and source materials. So the the main source materials of mercury at the site are these large tailings dumps that extend down to the creeks. The former furnace areas where they were actually, roasting the ore and distilling the mercury. And then in kind of the upper elevations of the mine area, the actual underground mine and the waste rock dumps that are still in place outside the underground mine. So those were the kind of the three sources of mercury. So in order to investigate that, the first thing we had to do was sort of map the extent of the waste rock and the tailings. And as you saw from that earlier slide, the site's very overgrown, so we kind of used traditional mapping methods to identify where the tailings were and put them on the map. But we also had to rely on a detailed LiDAR topographic map that we had produced for the project, which kind of allows us to see topography through the trees and see where there's tailings areas or not. And then we also used an XRF, an X-ray diffraction unit, which is an instrument where we can get almost an instantaneous reading of the metals in the soil. So we kind of use those things together to map in the boundaries of where this waste material was. And this is showing the Furnace Creek area. It's kind of zooming in here. Furnace Creek is kind of the drainage area for Furnace Creek is outlined in black there, and you can see the green stippled area. Those are where we've actually mapped the tailings, and they go all the way down to the creek, down to the confluence with Garut Creek. So that's kind of, but basically the green area is kind of showing where we've got mercury with tailings with really high mercury in Furnace Creek, and it kind of it's kind of consistent with the high concentrations of mercury we saw coming downstream in the surface water. So, we used that data. We mapped in the tailings for the whole site and the waste rock, and we used that data to select areas for systematic sampling, and we collected those samples and analyzed them in the lab for total metals. And basically what we found was that the soils, in the waste rock at the mine adit dumps had very high concentrations of mercury, and the tailings that were in the Furnace Creek drainage had probably the highest concentrations of mercury at the site. So based on that, the fact that we were getting really high mercury concentrations from Furnace Creek relative to the other drainage areas, and that we knew that we have really high concentration tailings in there, that's kind of led to EPA to decisions to take a removal action next year to address these tailings in Furnace Creek. And then also to, that there is a problem and that further work's needed downstream to look at, the impacts to the watershed and the reservoir. So I'm going to turn it over to Chris now, Chris Eckley from EPA, who's going to talk about mercury fate and transport and the reservoir studies.
Great, thanks, Howard. Okay, so I'm going to switch gears just a little bit here. So I'll start out to kind of contextualize the work that I was doing in Cottage Grove Reservoir by talking about methylation in general, to kind of provide the background as to how the work we did there fits into the larger mercury cycle. So regardless of what the source of mercury is, most mercury released into the environment from anthropogenic sources is in an inorganic form. So whether it's coming from a coal-fired power plant or whether it's coming from an abandoned mine like Butte Mine, it's being released in an inorganic form. However, almost all human exposure, particularly in North America, outside of industrial or occupational exposure, is through the consumption of methylmercury, the organic form of mercury, in fish. And so there's this disconnect between the type of mercury that's released and the media in which it's released to. Often a lot of the emissions of mercury, of course, are to the air. and the form that humans are exposed to, the organic methylated form. And so that requires an understanding of how mercury moves in the environment, how it's transported from this point of release to the point of exposure, how it's transformed from that inorganic form of mercury into the methylated form, and then how that bioaccumulates in biota that humans are ultimately exposed to. Throughout this talk, I talk a lot about methylmercury, and sometimes it's abbreviated MEHG for methylmercury. I'll point that out again. So a little bit more on the background. What is methylmercury? It's just mercury bound to a carbon atom with 3 hydrogens attached to it. And what that does is it makes it fat soluble. And so it's time that it spends, it can accumulate in our fat tissue, whereas inorganic mercury is water soluble. And so it has a much longer time period within our body. So if we're exposed to mercury, methylmercury, it can be in there for a couple of years and it can accumulate over time, whereas inorganic mercury is only a couple of days. So you would need to get a much larger singular dose of the inorganic form to have the same toxicological effects as methylmercury. Also, methylmercury is much more toxic than inorganic mercury. And where does it come from? It's bacteria that create methylmercury, and specifically bacteria that live in anaerobic or anoxic environments. Oxygen-free environments are where these bacteria live. It's primarily sulfate-reducing bacteria, which only live in places where there's no oxygen, such as the sediments on the bottom of a stream bed, or in a wetland that has really stagnant water is where you'd find these environments where you'd see a lot of methylation. And of course, as I mentioned before, methylmercury is a concern because that's the form of mercury that bioaccumulates in fish. Almost all of the mercury that we see in fish is methylmercury. People talk about mercury levels in fish. What they're really talking about are methylmercury levels in fish, because that's the form that bioaccumulates in the tissue.
Quick question, what's solubility of methylmercury? What kind of solubility is it?
I don't know. Do you know, Bryn? No, sorry. The solubility, yeah. Don't have those sort of numbers off the top of my head. Okay, so there's basically, in terms of how much methylmercury you get in a particular environment, it's a function of 2 main factors. One, the speciation of the inorganic mercury. So it's only a small fraction of the total amount of inorganic mercury that is actually bioavailable from the perspective of the microorganism that would do the methylation. And so if the mercury is bound to a cinnabar particle or a piece of mine tailing, the bacteria can't actually get that inside of them to methylate it. They can only methylate mercury that's already in the dissolved phase, and because they're primarily inhabiting sediments, it's that mercury that gets into the pore water phase, that amount, the water that is in between the particles in the soil. And so you need to get that mercury partitioning into the pore water or aqueous phase before the microorganisms are able to take it up into them in order to methylate it. So that's one of the main factors that dictates how much mercury gets methylated, is what is the speciation of that inorganic mercury. The other factor is, are there the bacteria present that can methylate mercury? They're not present in every location. There's these genes called the HGCAB genes, and those are the genes that are responsible for mercury methylation, and they're present in some sulfate-reducing bacteria, as well as a few iron-reducing bacteria and a couple of methanogenic bacteria. And so it's those combination of the bacterial community and the inorganic mercury speciation together which can dictate how much methylmercury you get. And of course, both the inorganic mercury speciation as well as the microbial community can be impacted by different landscape perturbations, such as reservoir creation or reservoir management, and mining activity, deforestation, things like that can all affect the activity of the microbial community as well as the speciation of the mercury at the site. Because I'm going to be talking about Cottage Grove Reservoir, I'm going to give a little bit of background on mercury dynamics in reservoirs. There's been numerous studies that have shown that reservoirs tend to have higher methylmercury concentrations in fish compared to free-flowing rivers and natural lakes. Some of the mechanisms for that are when you dam a river and you change it from a lotic to a lentic food web, changing it from a river-based food web to a lake-based food web, you often increase the length of the food web. And just that shift in the food web dynamics can allow for more bioaccumulation as the food web gets longer. So that's one of the factors. But also, when you have a reservoir, you end up with the potential for water to go anoxic in the bottom of that reservoir because the water's not free flowing, and you can actually get methylmercury production not just occurring in the sediments, but also occurring within the water column directly itself. Also, reservoirs tend to be depositional environments, so you get a lot of organic material as well as mercury that would otherwise be free flowing in the water being deposited and accumulating in the sediments where it has more potential to get methylated. And finally, one of the features of reservoirs, particularly reservoirs like Cottage Grove Reservoir that are used for flood control purposes, you have really wide or really large water level fluctuations. And what that can do is that it can take the accumulation of sulfide, which is the byproduct of sulfate reduction. So when those bacteria are doing mercury methylation, they are using sulfate and releasing sulfide into the environment. When that sulfide builds up, then those sulfate-reducing bacteria go dormant and they're no longer active, and other microbial populations become the dominant ones in the system. However, when you have those raising and lowering of the water levels, when you expose the sediments that have sulfide in them to the atmosphere, that sulfide reoxidizes back to sulfate, and you re-wet the system and you have a brand new store of sulfate. So you're effectively recycling the sulfate in the system, which can facilitate mercury methylation occurring there. So the study location was a Cottage Grove Reservoir, which I'm sure most people here are familiar with, about 10 miles downstream of the Black Butte Mine. And there's been fish consumption advisories in the lake since 1979, has some of the highest fish tissue mercury concentrations in the state. Perhaps the advisory action level, we should say 0.04 instead of 0.3. 0.3 is like the national value, and it's based on eating 17.5 grams of fish per day, which equates to about one fish meal per week or maybe one fish meal every other week, which is a really low rate of fish consumption. And so in Oregon, that 0.3 value has been changed because the fish consumption is no longer 17.5 grams per day, but 175 grams per day, which equates to a more protective level of fish consumption for people that are more frequent fish consumers, which is very common among West Coast populations, particularly tribal communities. And so then that results in an action level at 0.04. But regardless, there's even fish that are in Cottage Grove Reservoir that are above that 0.3 national value. So one of the questions, we have that inorganic mercury being released at the mine site, and then we have high levels of methylmercury downstream in the fish. And so there's several questions then that we need to answer. We need to understand what is the connection between the inorganic mercury being released at the mine site and the methylmercury that's accumulating in fish downstream. Questions that should be addressed are, where is the mercury being methylated? Is it being methylated at the mine site? Is it getting methylated in the Coast Fork Willamette River, or is it getting methylated in the reservoir? And if in the reservoir, where within the reservoir? What are the variables that control the methylmercury production? As I mentioned earlier, there's a lot of factors that affect how much methylmercury gets produced. Are the bacterial community that are methylating mercury limited by the availability of mercury at the site? Or is there more mercury than they know what to do with, and they're being limited by the amount of carbon at the site? Or are they being limited by the amount of sulfate at the site? And ultimately, if we want to try and decrease the amount of methylmercury in the fish, we need to understand what is the variable that is limiting methylmercury production in that area. And then the final question is, what is the source of the inorganic mercury that's being methylated? How important are new ongoing releases of mercury from the mine site versus legacy mercury from the mine that's been accumulated in the reservoir for decades? And how important is atmospheric deposition from sources that are coming outside this region? How am I doing for time, Bryn? Am I doing okay? Okay. I'll do a couple. I'll try and go a little faster. So we did this study where we looked at how the water level fluctuations in Cottage Grove Reservoir are affecting mercury methylation rates, and we measured at 28 different locations within the reservoir. And we measured during different levels of water in the reservoir and measured surface water, sediment, pore water, and we did some mercury methylation rates. And this picture here just shows kind of what's involved with collecting the samples. So we go out and we collect the sediment cores, and then we bring them back. We have this mobile lab that we drive out here. The people at the Village Green have been really, really nice to give us a place to park this, which has been great when we come out and do our sampling. And then inside there, we have an anoxic glove chamber. We do all the cutting of our sediment cores. We want to keep everything oxygen-free because we don't want to, we want to preserve the redox conditions in those sediments and not expose them to air while we're processing them. So we cut all the cores up in our anoxic glove chamber. We put them in a centrifuge to spin them, and then we were able to filter them and get pore water that we show there. And we also did these mercury methylation rates where we're using stable isotopes. I won't get into that detail there. I'll just kind of skip over that, but feel free to talk to me about that if you're curious in terms of the details. And now I'll go over the results really quick. Here's an example of what we see at changes in mercury and methylmercury with depth within the reservoir. So we got each one of our sediment samples that we collected and we cut it into different 2-centimeter increments. And if you look at the black line there, that's the inorganic mercury or total mercury concentration, and it's pretty consistent, but we see this different trend with sediment depth with methylmercury, with the methylmercury being much higher near the top of the core. And it's important because it shows that the methylmercury concentrations do not always follow exactly what the total mercury concentrations are, that you can have this disconnect, and that those fresh carbon sources and the water level fluctuations that are affecting those top sediments are resulting in higher mercury methylation there than deeper within the sediment. And then spatially, we've kind of divided up the reservoir into 3 different areas. There's that permanent pool, the part of the reservoir that is always covered with water year-round. And then you have these seasonal mud flats, which are that big area in the middle. And then right where the coast fork flows in, you have these kind of wetland areas that are more covered by vegetation. And there's pictures that kind of illustrate those 3. And so spatially, if we look at the total mercury concentrations, that permanently inundated pool has the highest concentrations compared to the seasonal mudflats or the seasonal wetlands. And the reason for that is because a lot of the transport of mercury from the mine site is occurring during those wet months in the fall and during the winter. And at that point, the reservoir is at its low level. So the Coast Fork River is essentially going all the way until it hits that permanent pool, and that's the depositional zone for when you get those high storm flows during the fall and the winter. But if we look at the trends in red here of methylmercury, we see just the opposite. The area with the highest total mercury concentration has the lowest methylmercury concentration. Those areas that are subject to the water level fluctuations have higher methylmercury. I'll skip over this just to go a little quicker. So here we have, from all of those different locations that we collected the samples from, we have the sediment methylmercury concentrations on the y-axis and the sediment total mercury concentrations on the x-axis. And one of the things that jumps out is there's a lot of spatial variability in terms of the total mercury concentration within the reservoir as well as the methylmercury concentrations within the reservoir. And we can kind of break these up into 2 different categories. There's the sediment concentrations that are larger than 1 microgram per gram, and we don't see much of a linear relationship between mercury at those high concentrations and the amount that gets methylated. But at the lower concentrations, we do see a fairly linear relationship. So it seems that at the really high mercury concentrations, you have a reduction in bioavailability of some of that mercury because it's those really the sediments with the highest concentrations are probably particles from that mine where that mercury might be more in a cinnabar form or a piece of tailings, and it's not bioavailable to those bacteria to get methylated at the same rate at which some of the mercury at the lower concentrations are. And this is, of course, important because when you're thinking about where at a site you want to remediate, you want to focus on the areas of the mercury that's getting methylated, and you don't want to decrease or expect a 1-to-1 decrease in methylmercury concentrations for the amount of inorganic mercury that you're remediating if you're not targeting the right areas where the mercury is more bioavailable. So I guess the last thing, well, I guess I'll go over that really quick. So the total amount of mercury in the sediment is shown on the x-axis, and on the y-axis we've got the pore water concentration. We see that there's not a lot of connection between the total mercury concentration in the sediment and the amount that's in pore water, and that's because different sediments and different sources of the sediments have different abilities to retain that mercury. Some of it's really tightly bound to the sediment matrix, whereas other mercury is more loosely bound and can go into the matrix, and that's important in terms of how much ends up getting methylated. And so if we're looking at just pore water total mercury to pore water methyl mercury, you start to see a linear relationship. So to summarize all this is my last slide here. There's this visual that I put together kind of comparing the permanently inundated sediments on the left-hand side and the seasonally, the sediments that have seasonal water level fluctuations on the right-hand side, and the size of the font of the different things in that picture kind of represent the dynamics, the relative magnitude of their importance. So for the permanently inundated sediments, you have more mercury bound to particles and less in the pore water phase, and that's flipped in the seasonally inundated sediments. And you have a buildup of sulfide, that's S2 minus, in the permanently inundated sediments, whereas you have that recycling back to sulfate in the pore waters of the seasonally inundated sediments. And I didn't show any data for this, but essentially, also when you have those water level fluctuations, you cause there to be more dissolved organic carbon, that's DOC listed on here, going into the pore water phase. And that also helps facilitate the microbial community, giving them a carbon source that's available. And the net result of that is more methyl mercury production in the seasonally inundated areas compared to the permanently inundated areas. So that's all I've got. Now I'm going to pass the microphone for the final few slides of the talk to Dave Tomten, who's the project manager for it.
Thanks, Chris. So now I'm really switching gears. So for the past hour we've been talking about the cool science that we've been doing. And Bryn talked about the global context. Howard talked about the investigations we've been doing at the Black Butte Mine. And Chris talked about the mercury dynamics in the reservoir and how the mercury is getting from the sediments into the fish. So what I would like to talk about is the really cool stuff that we're going to use this science for. We're going to use this science to make decisions about what we're going to do next to fix the problem. And I guess I wanted to just say there were like two take-home messages from all the science, in my mind, two key take-home messages from all the science that we've been doing. One take-home message is that the level of mercury, methyl mercury in the fish is a public health concern, and we need to fix that problem. The other take-home message from all the science that we've been doing is that a big part of that load to the watershed is coming from a very small portion of the Black Butte Mine Site, the Furnace Creek intermittent drainage, which is a 2 to 3 acre area in a much larger site. And so over the past year, we've been trying to figure out what to do with, to reduce the loads in the Furnace Creek area. And we did a planning document last fall. Some of you, I see a few familiar faces from our public meeting last fall, but we did a report that evaluated different ideas for fixing the problem in the Furnace Creek area. And then after that meeting, we were told, forget about it. There's not going to be any money in the next year or several years to fix the problem. But then 2 months ago, we were told, well, we have some end-of-year money. If you guys can scramble and put together a decision document and get the money into a contract, we can get some end-of-year money to implement the project next year. So we've been going like crazy for the past 2 months to wrap up some planning documents for the Furnace Creek area. And just 2 weeks ago, we signed what's called an action memo to which selected an alternative for cleaning up that Furnace Creek catchment area and addressing that small area that contributes half of the load to the watershed. It is pretty cool stuff. Anyway, this is a picture of Furnace Creek, and it's dry most of the year. It's a gully with contaminated material on the north side of the gully and in the bottom of the gully. And it's got unstable slopes that are eroding into the bottom of the gully. And that's mine tailings that's eroding into the bottom of the gully. And then during storm events, you get delivery into the watershed. And I've already talked about these key messages. So we signed an action memo 2 weeks ago that selected an alternative. We're going to go in there next summer. We have about 3 months of work lined up. And we're going to scrape out the tailings that are on the surface in about a 2 to 3 acre area and put them in, basically excavate about 6,000 cubic yards of tailings and soil and contaminated sediment and put it into an on-site repository. And then we're going to go back to the areas where we've done that excavation and grade and shape and rehabilitate that area with native vegetation. And while we're doing that, we'll do sediment control, best management practices. And sometime next fall, I think we'll have that work wrapped up. And the cost of that project is about $2 million. And that was all kind of end of year money. Yes?
And who pays for that?
That's taxpayer money.
And who caused it?
Well, there were a series of mining companies that were active at the Black Butte mine during its 70 or 80 year history. And we've actually looked at the succession of ownership of all those corporate interests at the site and tried to track down leads to find out whether any of those companies had successors that were still in business, and all those leads dead-ended. So, most of the projects I work on, we can track it to a company that's still around, and we can bill them for the work. At this site, we couldn't find anybody that was still around. And so, next step. I'm sorry, I can't hear you.
Did you define the repository, the specifics of the repository, and how that will deal with the problem?
And so we did some work up at this site in 2007 on a different part of the project, and they created a pile of tailings in kind of a flat area in the middle of the site on top of an old tailings pile. And what we're going to do as part of this project is increase that pile of tailings. We're going to grade it. We're going to add 6,000 yards of tailings to that pile. We're going to grade it and shape it and cover it with a foot of soil that we're going to bring in from an off-site source. That's our repository. And then this is all part of an interim action. This is a partial fix for a much larger site. And so the removal action will be done next summer. And then at the same time, we're going to continue planning a final remedy for the site that'll be a more complete and permanent fix. And as part of that remedial action, we'll look at all the work that was done as part of this interim action, which might include some additional improvements to that repository.
Even though you capped it with other soil, won't the rain still permeate through the soil and wash it into the stream eventually? Perhaps in lower concentrations, but
Yeah, well, that's a really good question. And I mean, maybe Howard can answer that. But, like I said, this is a temporary solution, and we'll look at whether that cap is adequate as part of the full remedial action. But we don't see a lot of mercury in the groundwater at the site. I mean, the surface soils going down for 50 or 100 feet are highly weathered, and they've converted from volcanic rock into clay materials. And we just don't see a lot of contamination in the groundwater. But we have a well near that repository site. We're going to continue to monitor it, and we'll look at the effectiveness of that cover after the removal action is implemented.
So the question I have is whether you're going to have more contamination after you go in and disturb everything than what you've got right now with everything having sit there for 50 years.
Well, I mean, did everybody hear the question? I mean, the question is whether we're going to make the situation worse by doing this construction work. And we've considered that as part of our planning documents. And we think that when you do this type of construction, it's never going to be 100% effective. You're not going to reduce the release from this much per year down to 0. We expect to reduce it significantly, and we think that the work we're proposing to do is going to work. We looked at a series of alternatives, scraping it out and rehabilitating the area. We also looked at capping the area. We also looked at a strategy that involved in-place stabilization of the tailings. And we selected the alternative that is the most thorough and the most expensive. And we think it's going to work. And I've done a lot of this kind of work at other sites over the years, and I think this is the best way to go.
So, how does that compare with Champion Mine and the restoration position of tailings there?
Are we done? Do you want to go ahead and start Q&A?
Can you just repeat the question into the microphone so everybody hears it?
Yeah, do you want to?
So I think we're at Q&A right now, I assume, right?
Seems like it.
Okay.
Do you have more that you need to cover?
I think we're there.
Okay.
So we'll go through Q&A now. So the question was, how does this compare to Champion Mine? Champion Mine, as a lot of you probably know, is Forest Service land in Bohemia District, and that's a former gold mine, I assume it's a gold mine. It's a very similar type of project. I mean, basically it's the same idea. They go through a process just like Dave was talking about, where you look at alternatives to clean up. You decide based on a number of balancing factors like cost, protectiveness, long-term, all this stuff. Implementability, is it going to be safe to implement? Are we going to have problems down the road? Is it going to last for a long time? So basically it's the same process. Champion Mine is dealing with a different issue. It's acid mine drainage, which is a different it's just a different type of geochemistry issue than when we're dealing with mercury. Here we're talking about particulate load of mercury moving downstream in suspended stormwater, that kind of thing. Champion Mine is acid mine drainage, where you've basically got sulfides in the groundwater, and as that groundwater starts to come out of the adits and portals, it essentially is very low pH. It's very acidic, and it also drops metals out as it goes. That's where you get the red and yellow colors. So their treatment action is a lot different than this one. It focuses on trying to change that pH chemistry so that you actually get a neutral balance before things start to drop out downstream. The other thing is that Champion Mine and those issues are more of an ecological risk issue as opposed to mercury here, which is more of a human health risk issue. So, but it's a really interesting question because we do have a lot of sites in Oregon that are acid mine drainage, and then we have a lot of sites that have mercury runoff. And there's really only one site in Oregon that I've seen that has both of those, and it's down in Jackson County. And it's kind of small, but it's just kind of, they often don't seem to go together. Question?
There's a residence that's right nearby there. Will they be impacted in any way?
The question is that there is a residence next to Black Butte Mine, and the question is, will they be impacted by this? Well, the residence is immediately adjacent to the property that the mine site itself is on, and they have been there for a number of years, and they are sort of affected by this because there's a lot of activity, work that's going on, and in fact, there may be some tailings that are on that property, and that is something that Dave and I were talking about today, and it looks like the EPA is going to be looking at that and seeing if they can do any kind of work to fix that on that property. So, there's a lot of questions here. Do you want to? I don't remember. Can you want to keep track of who's? And by the way, you guys, just I'm not the only answerer here. If you guys want to ask questions, please. You know, we have other folks. So.
Live in the house closest to the lake. I'm on Reservoir Road, and right across the road from the lake. I have a small house with a shallow well. It smells like sulfur every now and then.
Hmm.
In my institute, should I be also looking for mercury and sulfur and other organic and E. coli and what have you in my water when I get it tested?
Yeah. So that's a good question.
What's going to affect? We talked about mercury in the fish. Well, I'm a first one. That's one of my worry about it in the
Right, good question. So the question was, what's going on with groundwater around the lake? Essentially, there's wells out there. I think a lot of people know that there's high arsenic in a lot of the wells, which is naturally occurring. We have not done any work on groundwater monitoring around the lake, but I guess I'll look at my colleagues here. Up at the mine site, we're seeing very low concentrations of mercury moving into groundwater. So based on that, I would assume that the methyl mercury in the reservoir is also not moving out into groundwater. But I'd actually defer this to Chris to see if he's got some ideas on that.
Yeah, thanks. That's a good question. In terms of the methyl mercury concentrations in the water in Cottage Grove Reservoir, they're surprisingly low. It's a little bit of a mystery as to how the fish end up having some of the highest methyl mercury concentrations, while the water concentrations in the reservoir, they're about, all of them that we've measured have been less than 1 nanogram per liter methyl mercury, and often they're about 0.5 nanograms per liter methyl mercury. And the water quality standard that's made for protecting mercury accumulating in fish tissue is at 12 nanograms per liter. For drinking water, it's, what is it? Does anybody at that table over there know? I think it's 200. Yeah. It's 200 nanograms per liter. So we're typically less than 1 nanograms per liter in the reservoir. So in terms of a direct drinking, a risk from directly drinking the water, we're way, way, way below any health criteria associated with that in the reservoir. And also what we've measured in the groundwater has also been, by the site, has been typically below that 200 nanograms per liter value. So really the main risk is the methyl mercury has to get accumulated up several levels of organisms in order for it to reach those concentrations where there is health concerns. Yeah.
Has there been any consideration given to the thousands of tons of cinnabar that have been removed from that site over the years and used as road base throughout that whole upper area?
I think this is for me. So the question is, has there been any consideration regarding the thousands and thousands of cubic yards of tailings that have been removed from the Black Butte mine and placed in roads, in foundations, and other things like that? So that is a question that the state has been wrestling with for a while. As you may know, there's a railroad grade in the Sutherland area that was made out of Bonanza mine tailings. That is really the only site that we know of specifically that we know that there was mercury mine tailings used for road construction, and we're dealing with that as a cleanup project. In this drainage, with regards to Black Butte mine, we don't have any knowledge of that. We've done some outreach. Oregon Health Authority has done some outreach on this, and we've gone out to the community and asked if you know of it, let us know, or whatever. We'll do what we can to fix it. But the problem is nobody wants to come because it basically could become a cleanup site. Yeah, and that's another thing. We can assume that there are a lot of roads are basically constructed out of that. It was basically free material at the time. And there was an anecdotal piece of information at Black Butte Mine that some of the tailings were taken up to I-84 in the construction of I-84. And so, we don't know where it is, but the way we're dealing with it is if we don't know, if people want to come forth and tell us, then we might be able to deal with that at the time. On the other hand, one of the things I should mention is that the Red Rock Road in Bonanza area, we're working on that site, and the main risk drivers there is actually arsenic within the tailings. It's not the mercury, because a lot of the mercury was removed. And the other thing about that is the arsenic is often not very bioavailable because it gets bound up with oxides and other types of chemical forms that reduce its ability to actually get digested in the human system. So, and we're wrestling with that still, and we're working on that site. But it's kind of that's about as good as I can answer for that sort of thing. Green?
So thank you for being here. I live on the east side of the reservoir, and it's been on my mind a lot. So this is fabulous. Thank you.
Thank you.
A lot of questions. So the swimming, you answered that. Shouldn't be a problem with swimming. Young children swimming in the reservoir looks like it's an issue. What about further down? Going over the dam. What's the mercury accumulation happening in the water when the river is actually there? Is there much?
Okay, that's a good question. And I might even defer to somebody here who might be able to tell us a little more about that. But the question is, what is happening with the mercury from the reservoir moving downstream? What do we know about mercury downstream in the Willamette? I can tell you back in 2006 when we did there's a big Willamette strategy. Governor went up to the mine site and we did a lot of sort of public outreach. There was concern about mercury from the Black Butte mine, but there was also concern about mercury from a lot of other sources throughout the Willamette, and it becomes a somewhat complicated system. But I don't know, Chris, or Paul, if you want to make a comment about that, about some of the stuff you know with regards to, it's maybe Chris? Can I answer that? Thanks.
Yeah, well, a lot of the really high mercury concentrations, I think Howard's talk, his slides touched on this a little bit. Most of it are bound to particles. And so the reservoir, Howard might know off the top of his head, but I'll say over 90% of the mercury that's mobilized from the mine site is bound to particles, and only a small percentage of it's in the dissolved phase. And so a lot of that is just accumulating behind the dam. And there is definitely mercury being exported from the dam, but those concentrations of total mercury are much lower than what's coming into the mine just because it's settling out in those sediments behind. However, you do have methylmercury production within the reservoir that's larger than you would have in the upstream area. So the reservoir itself can be a source of methylmercury to the downstream environment. Methylmercury has a shorter lifetime, like with just inorganic mercury. Because it's an element, it can't be created or destroyed. It's in the system and is going to remain there and can be transported, all the way down to to the Pacific Ocean. Whereas methylmercury can be reduced by exposure to sunlight and oxygen. So you're constantly having methylmercury being created and then methylmercury being destroyed, demethylated as it moves through the system. And we haven't actually got to that point where we're answering that question of how far downstream of Cottage Grove Reservoir do we see methylmercury that can be traced to that source. But that's a question that we'll eventually be addressing. Yeah.
I'm assuming that not all fish absorb methylmercury and treat methylmercury the same. So are some fish healthier to eat than others? For people who are fish.
Yeah, that's a great question. So the question was, are the methylmercury levels similar in all the fish species, or do some fish species have higher methylmercury concentrations than other fish species? And that's definitely the case. Yes, it all depends on what the foraging behavior is of that particular fish species, and how high it is on what its trophic position is. If it's a fish that's eating benthic invertebrates and it's a primary consumer of those, then it's going to have lower concentration. But if it's a fish that's eating the fish that ate the benthic invertebrates, then it's going to have an order of magnitude higher methylmercury concentration. And so you can definitely, within the lake, you can get huge differences in methylmercury concentrations between different types of fish species depending on what it is they're eating and what they're feeding on. And then also the foraging behavior of the fish. Some of those slides that I was showing earlier show that that area near the wetlands has the highest methylmercury concentrations in the sediment. So fish that are specifically feeding in that area of the reservoir would be exposed to higher methylmercury concentrations than individual fish that were feeding in other parts of the reservoir. That's a good question. Off the top of my head, I don't know. Are you familiar? Oh, I'll pass to Bryn here.
Sorry. So from the data set that I've looked at, that we've been basically collecting since at least the 90s, largemouth bass is the highest. 1.79 milligrams per kilogram is the highest we've seen in Cottage Grove Reservoir. It's the highest in the state, other than East Lake in Newberry Crater, which actually has higher fish concentrations, but that's most likely due to geothermal, natural inputs of geothermal activity and mercury. So trout is often less than largemouth bass, quite a bit, and that's kind of all I know. I'm a geologist. I don't put much time into that. But I will recommend that you take a look at Oregon Health Authority's Fish Advisory webpage. You can do a quick search for that. They have reservoirs throughout the state with all that information on it. It talks about the different species. So you're welcome. Oh, real quick here and then there. Okay?
So my concern, or my question is concerning irrigation and transportation of mercury through maybe sediments to agricultural areas. Do plants uptake mercury, and is that a concern?
Ooh.
For consuming plants?
That's a great question. So the question really is, do plants uptake mercury in their tissue through the roots and up into the... I'm not an expert on that. I have read some documents about heavy metals and transport. Arsenic obviously gets into rice. We've seen that internationally. Yeah, okay. I was going to say, I think somebody here might know that.
Sorry, not to hog the microphone. But fortunately, mercury is not taken up very readily by the roots of plants. So you can have plants growing in fairly high mercury concentrated soils, and you don't see that manifesting in the plant coming through a root-based mechanism. However, mercury is volatile. So when somebody breaks a thermometer, people are concerned about inhalation of mercury vapors from that. So mercury in the tailings at a site or mercury in soils are constantly volatilizing, albeit at a very low rate. We're talking nanograms per meter squared per hour. I mean, a couple nanograms per meter squared per hour. But if you have really highly concentrated soil concentrations or tailings, and you have plants growing on those, you can get elevated concentrations in the leaves, but it's coming from soil emissions and then uptake into the stomata, into the plants, but not coming in through the root system. So in terms of irrigation with water, the water concentrations coming from the Willamette River, the Coast Fork Willamette River, are quite low compared to what concentrations we see in the tailings directly. So if you applied the water from the Willamette River to fields, I don't think that would be an issue in terms of uptake. The concentrations just aren't high enough to see a significant amount volatilizing from that water and then getting into the leaves.
How about bioaccumulation in fungi?
Okay. Oh, sorry. Yeah, you can do your question, then I'll come to you next. Sorry about that. Yes? Sorry. What is your question?
My question is bioaccumulation in fungi, mushrooms, biomushrooms, contamination.
Oh, that's a really good question. That is something that the question is about mercury bioaccumulation in fungi, in mushrooms. And we don't have any data on mushroom concentrations at the site. My guess would be that they're not particularly elevated, but just because you don't get much mercury uptake into plants from the roots. But it is possible that they could have elevated concentrations. I know that people have done studies on lichens that have shown in mercury-contaminated areas, the lichens tend to have a signature because they're uptaking the air from the site. So that is a good question, but we don't have data on that at this point. Sorry for the delay. Yes, your question? The question is about the fish concentrations, and I'll put that to Bryn. Are you the best source?
I guess. I think I am. So the fish... Oh, the health of the fish. What is the health of the fish? Not the concentrations of fish in there we check. I gotcha. Yeah, no, I don't know much about that. That's a good question. My suspicion is that they're fairly healthy and they just have contamination in them, and it's at concentrations that are bad for the human when they ingest it, but not necessarily bad for the fish. But that's all I can.
Yeah, there, there isn't, looking at the kind of sublethal effects on biota is an understudied area of research. There are people that are getting into that, but the concentrations, like when you get up to some of those higher concentrations that are like over 1 microgram per gram, that's in the range that researchers are starting to see sublethal effects on the fish themselves at those concentrations. So that's not, the fish aren't dying from that level of mercury, but they might have decreased reproduction, or they might have decreased ability to avoid predators, that sort of thing. And that's an area that I don't think there's a really defined number at what concentration do you start to see. This is still kind of in an area of active research. So much of research on mercury pollution is focused on humans first, and at what levels do you see effects on humans? But there's becoming more and more interest on wildlife exposure and what the impacts is. Probably the most well-studied species are loons, because they eat so many fish, and fish consuming birds that are eating fish for every single meal definitely have been observed to have negative health effects because of mercury exposure at the same sort of concentrations that we're observing in Cottage Grove Reservoir. None of that work has been done in Cottage Grove Reservoir itself, but from other studies, we can assume that there probably are some subtle sublethal effects on wildlife. Are there any other questions? Yes, back there.
Howard, do you want to answer that? That's probably a good one. That's a great question about.
Yeah, Aaron, you can repeat the question.
Yeah, the question was, at the mine site, are there certain areas or generations of tailings that have more or less mercury than others? And that's a good question, and I didn't really get into it in my discussion, but this focus on Furnace Creek is related to that. Furnace Creek was the tailings at Furnace Creek were from an earlier phase of mining and mineral processing with a less efficient extraction of the ore. So the tailings there, we're seeing much higher concentrations, anywhere from hundreds to thousands of ppm mercury, whereas the other tailings from the newer generation of mining are, tens to hundreds of ppm. So it's a good question.
One last question right here.
Yeah.
Thanks. Just to quickly summarize that question over the microphone or the comment, making the point that fungi do accumulate metals, other metals as well as mercury, and we do. And I guess when you were answering the question earlier, I don't mean to imply that there's no mercury at all accumulating in fungi. Certainly there is, and certainly there's some mercury uptake into plants by the root pathway, but it's kind of an order of. Is it accumulating to the point that it becomes really highly concentrated and it becomes an exposure risk? But certainly there is some mercury uptake into plants and fungi and lichens included. I think that's the last question that we have time for, but I'm going to be around. I don't have any place to go tonight, so I'm happy to answer any other questions that people have. Just please feel free to come by and ask me any Mercury questions that you have, and I'd be more than happy to answer them. And I'll pass the microphone off.
So real quick, you guys, there's some fact sheets that Dave brought on the back table for the mine site, and there's also some information about signing up for updates and getting more updates on the site. So I think we're done. Thanks everyone for your time. Good. Thank you. No,